And our next speaker is David, and he will talk about visiting checksum offloads inside OVS.
Hello. So my name is David Marchand. I'm a TPDK maintainer. I've been working on OVS user space database quite a bit. And so I'll be presenting some API changes that happen in the 3.6 version and some more changes I'm looking at. So briefly, the agenda is quite simple: an introduction, the existing API, the new ones that got merged, and the new changes. So, what are we talking about? We are talking about TSO support in the user space database. So it's been a long road, let's say. It started with OVS 2.13, where we first started to implement TSO for DPDK devs. After this, there were more features added in it with UDP and SCTP checksum, non-DPDK dev supported. Later in 3.2, we started enabling hardware offloads, checksum offloads, let's say. It's better like this. And so across the version, we added more and more. And at some point around 3.3, there were some issues that were identified in the API. And so in 3.6, I started to clean this up. And so I will present this. And as part of this rework, I did some benchmarks and I identified some issues with auto UDP. So it will be the second part of the talk. So what was the offload API in 3.2? It was mapped initially on the DPDK API, which is based on the number of flags that you set on the takes, well, for fitting the takes descriptor of your driver. So as part of it, OVS was filling those takes flags in the all flow from the reception to while processing the packet until you send it to the driver. For DPDK drivers, it meant that since they were providing some status on the packet, there was a translation that was put in the flow extraction, and it was maintained all across the data path. So it was for basic TSO support. There was no tunnel at the time in 3.2. So in 3.3, we added tunnel support. And as part of it, it became more complex because the DPDK API was expecting us to tell, oh, I want to do outer UDP checksum. And the checksum will be implicitly inner checksum. Okay. So as part of the processing in OVS, we had to remember, oh, what am I going to do in the end? Is it for outer? Is it for something else? So yeah, it became a bit complex. And the problem also was that it contradicted something else in OVS. We were tracking everything as inner offsets, while we had to maintain outer flags for the final transmission. So it contradicted this logic, and we had a bug where we had some crashes after recirculation. So the fix in 3.3 was to simply disable the support of this feature after recirculation. There were also some other use cases that were not supported well with the approach, where if you had some tunnel in your virtual machine and you were pushing packets to OVS, OVS was not able to tell if the tunnel encapsulation was in OVS itself or where. So there were some cases where offloads were not behaving correctly. So what happened in 3.6? First thing, we added a lot of unit tests. We had a big gap on this topic, and so part of the work was revisiting from scratch and separating, let's say, error status from the takes decisions in the data path. As part of this unit test, some coverage counters were added. It's interesting because if you need to look at checksum, what is happening in your data path, you can look at those counters outside of the unit test. Is still interesting if you want to see that there were some evaluation of your checksum in which part of OVS. So here we go. First thing that was done, so everything was, the checksum flags were stored in a field that comes from the DPDK mbuf. So it's a structure that is embedded in your DP packet. And so everything was mixed in it. So the first thing that we did is isolate and declare a new field where the other modifications were added. This field is simply called offloads. Maybe not a good name, but I'm sorry, I'm not a good. Yeah, I'm French. I don't have a lot of ideas in English. So yeah, this field was added with two parts. It's a 32-bit field with the 16 lower field for the outermost checksum and the higher part for the innermost checksum. But since we need to translate from the DPDK API, I did a bit of, I put some, let's say, bias for, I have some bias for DPDK. So I help the DPDK driver and just align the inside bits to the DPDK API. Yes. As part of this API change, so tunnel flags were set in the encryption code in OVS, but rather than setting the DPDK API flags in OVS, I simply added a metadata in the offload fields to know that we are in a tunnel. And then it is the responsibility for the transmission driver to translate it to its own API. So it became the responsibility of native DPDK, and it can be native Docker or native Linux to implement its own stuff. On the IP checksum side, so I kind of took the same approach as DPDK, but in the end, it was already the case kind of in OVS before the changes. So there are 4 status. The first one is the unknown status, what it is. Actually, it's simple. If a driver is not able to tell, well, it's for OVS to check, if anything. The second status is bad. So when a packet is received, if you know that the status is bad, it's better for OVS because there is no need to check it. But what is important is that we took the approach globally in user space datapath that if a packet has a bad checksum, any modification on the packets through the OpenFlow pipeline must result in a bad checksum as well. We don't want to fix stuff because it would be hard to understand why it happened. The good status, well, it's a good status. A good status means that the packet has a good checksum in the data, and you're supposed to transmit it with a good checksum as well. And finally, so the new status for IP is a partial one, which is interesting for virtual drivers because usually they can say that the packet is correct, but they don't want to spend time computing the checksum, and they want to rely on hardware offloads. And that's it. And so, yeah, the important point here is that this status is that of the outermost IP header when you are looking at the packet. Thanks to this outermost property, we can now just we don't have anything we don't need to track any takes flags anymore, and we don't need to care about it, whether it is outer or inner. We are just looking always at the outermost header. So there's nothing to do in the flow extraction. For encapsulating, we also need to track inner status. So what we do is simply shift by 16 bits. So it's quite easy, and you can go you can shift on when encapsulating, and if you decapsulate, it's the other way. So it's easy to do. And yeah, like for tunnel flags, since there is nothing done in OVS for the takes flags, it's for your driver to implement the right API at the end. And actually, the driver only needs to look at the partial status, because if it is bad, the packet is already bad, there's nothing to do. If it's good, that's the same. And usually you will not get any unknown status at your driver level. For layer 4, well, it's the same. There is no difference in the status, nothing much to add on this topic. Yeah, just one thing. We still track the protocol. It's simply to avoid reparsing the packet at layer time. So we have this little bit that is set as part of the offload flag, offload field. Finally, the TCP segmentation. So yeah, we had two information in the TP packet. It was the segmentation size and that we need to do a segmentation. Well, actually, it does not. We don't need this information, so it was removed as well. So the impact of the series. So we went from an OVS which was preparing early the takes flags as part of the reception and the flow extraction and maintaining this in all the processing and finally calling the drivers. So all of this was separated. There is nothing about the takes flags in the processing. It's only now on the NetDev implementation when transmitting. So we moved a lot of code from the core of OVS to the drivers themselves. Because of this, there was some more complicated conversion in the NetDev DPDK driver, for example. So it impacted the performance a bit for packets that were not touched at all. So we implemented a little optimization for just the IP checksum stuff. And thanks to this, we actually got better performance overall when not touching the packet at all, which was interesting because initially the series was more about maintenance and getting something easy to read and not really about performance. But still, we had a little enhancement. Yeah, some numbers with 3.6. So I did two couples of numbers here. First part is with, so it's all IPv4 Geneve tunnels. The first part is with no UDP checksum on the tunnel header. So we can get with the usual NICs. So I have some Mellanox, NVIDIA, ConnectX-6. Sorry, I'm used to Mellanox. Yeah, ConnectX-6, the Intel E7, X7 series and Intel E8 series. So all of them behave kind of the same. As you can see, it's only for, I'm sending packets from an iPerf to another one through Geneve tunnel. So the numbers are not really stable because, I'll get to it later, but because of the way packets may be dropped on the receiving side. But overall, the three type of NIC got similar performance. But what is interesting is when I enabled outer UDP checksum on the tunnel header, I suddenly saw a large decrease in performance for connected 6 and for Fort Vale NICs. So the reason, outer UDP checksum. Those NICs are, well, the two ones are not supporting outer UDP checksum. Only the Intel one is supporting it at the moment. So outer UDP checksum, this is what I've been looking at. But first of all, I started by adding a lot of new unit tests because we were not checking implementation of the checksum offloads with tunnels. And so when I started looking at it, I realized that we were requesting some outer UDP checksum for packets that have nothing, well, we cannot do anything to them. By this, I mean, if you don't know what is in your inner part of the packet, well, you can just do a global UDP checksum without requiring any tunnel awareness from your driver. So this kind of stuff is easier with the new API. You don't just need to mask some bits. So yeah, for those, you don't need auto UDP checksum. But then when you do TSO, well, you will need the hardware to do something about the outer UDP, since it will be responsible for segmenting the packet and so updating the packet. So I was looking at this issue. I spent some time looking at the kernel database because they were doing something that I could not understand. So I already complained to Simon about it. But then after looking at TCP dumps, I ended up noticing that the checksum were always the same for some type of packets. And after looking a bit more, I realized that it was linked to the size of the packet. So everything was actually the same. If you add a longer packet, your checksum would just decrease in the opposite order. So why is it the case? Well, if you look at an encapsulated packet, so your initial packet is here, the inner port, and you put an UDP gniv header. So you want to checksum the UDP payload. But then you realize that if you do this as part of the packet, there will be a checksum in the IPv4 header. And if you do a checksum on this, it will equal to 0. For the TCP and data payload, it's kind of the same. So it's a bit simplified, but let's say that if you just do a checksum on the TCP plus the data payload, then it's 0 as well. So in the end, you only need to do the checksum on this part. And this is an optimization that I've been working on. Thanks to this, so yeah, I put a reference to the patches if you want to look. If you do just this, it already helps with the performance. I could get some more gigabits on this connected NIC. But then we still have software segmentation. So we want to rely on TSO. So, but what is TSO? So TSO, you take your packet and you want to have the NIC segmented by a certain size. And if yes, there's a bit more than a segment size at the end of the segmentation, you expect to have the rest. The hardware, we update a number of fields in the packets. So all of this will impact the UDP checksum. But if we want to apply the optimization that I explained earlier, what we can do is that we can isolate the non-multiple part of the packet, create a big packet with payload that is multiple of the segmentation side and applies this optimization. So the part with the rest is something that I'm not really comfortable with, because I would expect that the kernel always send TSO requests of the multiple, but I've seen occasions where I still have a bit of packet. So it's something that I need to understand maybe, and others will have idea, I guess. Okay, and then thanks to this, we can use hardware segmentation. And what is nice is that we can reduce a lot of consumption of cycles. So with this, there is no more, well, a little bit of partial segmentation. But overall, yeah, we went from 6 something to 10.4 gigabits for, yeah, almost a third of the CPU. Yeah, I just forgot to mention, all those numbers were done with only one PMD thread. So yeah, it's supposed to scale if you put more CPU. And yeah, that's it. Next step, so getting this optimization merge, I guess. After this, I would like to improve a bit what we have in OVS, because I've been fixing bugs on driver side a bit, and it's always a pain to add my custom patches. I would have to have something generic in upstream OVS. Next step, yeah, I'm looking for inputs if you have more use cases on the TSO and checksum side, if you have some missing stuff. And yeah, finally, do we mark this feature as non-experimental? It's been a long time. Honestly, the API itself, since 3.6, I don't see anything to change. So yeah, it's open for discussion. And that's it.
Any questions for our speaker?
Thanks for the presentation, and also for working on TSO. My question is, can you talk a little bit about the support for the other devices? You focus a lot on the DPDK interfaces, but we also support in user space like tap devices and the internal ports.
Yes, so I did not look at tab device yet, but we could, I mean, the infrastructure is there. If there is more APIs on the kernel side to simplify tunnel support when going through tab device, we could use it. It's just a matter of writing the NetDev Linux conversion to the right API. I know that there were some changes recently on the NetDev side for tunnels, I guess. So yeah, we could make use of it, but I did not have time yet to look at it.
Any other questions?
Are any of these changes, improvements already part of like deployed OVS, or is this just DPDK or OVS?
It's OVS user space.
Yeah. So is it like shipped to customers already?
No. So
I missed that.
offload API has been changed in 3.6, but all the optimization I have presented in the second part is to be defined.
Okay, thanks.
Yeah, speaking about changing the status, the support status, I agree with you that it's been a while that TSO is there and it's been used. We found some bugs, especially when focused on the tunnel part. That was like a known issue for us. But otherwise, I don't think we have seen bug reports in the mailing list, right? So
no, on the feature itself, it's working.
yeah. and it's enabled by default.
No, it is not.
Okay, so maybe
It is not. It is not enabled by default because well, we still have some little issues with the host user ports. No, it has been addressed with the changes. So we could maybe reevaluate this and enable by default.
Yeah. Okay.
Seems like no more questions, so I think we can head out to lunch.